Hello guys, welcome to my channel, and in this video I'll explain you article number 2.10 Dielectrics and Polarization. So we'll understand the meaning of both the terms. So I'll explain the NCERT to you line by line. So let's start. Dielectrics are non-conductive substances. Okay, so dielectrics are insulator basically. Okay, in contrast to conductors, they have no or negligible number of charge carriers. Okay, so we have seen in conductor what happens. There are mobile charge carriers, like in metal there are electrons which is free to move. Okay, but in case of dielectric insulator there are no charge carriers. Okay, recall from section 2.9 what happens when a conductor is placed in an external field. The free charge carrier move and charge distribution in the conductor adjusts itself in such a way that the electric field due to the induced charges opposes the electric field within the conductor. Okay, so we have seen in earlier that if I place a conductor in an electric field, suppose I place a metal in this electric field. Okay, so what will happen? There are electron free charge carriers that will experience force and they are free to move. Okay, they will experience force by this formula. Okay, in the opposite direction of electric field, so they will move opposite to the electric field in this direction. Okay, and there will be positive charge here, so there is a induced electric field opposite to the direction of the electric field. Okay, and this is equal to the external field. So what is the net electric field inside the conductor? That is zero. We have already studied this. Okay, so the charge is distributed in such a way that the electric field is zero inside the conductor. Okay, this happens until in the static situation the two field cancel each other and the net electrostatic field in the conductor is zero. Okay, in a dielectric this free movement of charges it not possible. It turns out that the external field induces a dipole moment by stretching or reorienting the molecules of the dielectric. Okay, so in case of insulator or dielectric there are no free charge carriers, so there will be two type of possibilities here because there are two types of dielectric. One is polar and one is non-polar. You know what is polar molecule? You have studied in chemistry. So a polar molecule is one in which there is dipole by itself. This is called intrinsic dipole moment. Okay, like you see HCl. What is mean by dipole moment? They have dipole moment, that is they don't have a their positive and negative center do not coincide. Okay, and in case of a polar molecule, in case of a non-polar molecule like you see H2 and CO2, the positive and negative center coincide. Okay, so electric field, when we apply electric field in non-polar molecule, what will happen? The electric field apply force on this positive or negative charge. Okay, the negative charge will be, there will be a force in the opposite direction of electric or negative charge, so it will stretch. Okay, the dipole will, the molecule will stretch like this and a dipole moment will be induced. Okay, this is the case of non-polar molecule. But in case of a polar molecule, what will happen? It itself has a dipole moment. Okay, so the electric field will orient this dipole, but this dipole moment are in random direction. Okay, these are on random direction, but the electric field reorient this dipole in a particular direction, that is in the direction of the electric field. Okay, so the result is that in both of the cases there will be a net dipole moment. Okay, and therefore a net electric field. Okay, that is called the induced electric field. But remember, this is not due to the movement of charge, but due to either orientation or either the stretching of the molecule. Okay, so there will be an induced electric field. And one thing more to remember is that this induced electric field is not equal to the external electric field. Like in case of conductor, those two electric field, induced and external, are equal, so the net electric field is zero inside the metal or conductor. But in this case, as they are not equal, so there will be the difference of these two. Okay, there will some electric field inside the conductor, but its value will be reduced. Okay, because the induced electric field is opposite to the direction of the electric field. We'll look it in detail further. Okay, for now there will be a electric field, induced electric field. The collective effect of all the dipole moment is net charges on the surface of the dielectric, which produce a field that opposes the external field. Unlike in a conductor, however, the opposite field is so induced does not exactly cancel the external field, it only reduces it. This all I have explained now. Okay, so now the extent of the effect depends on the nature of the dielectric. To understand the effect, we need to look at the charge distribution of dielectric at the molecular level. Okay, so I have already explained all this, so I'll just read it and you will get the whole idea. Okay, so the next paragraph is the molecules of a substance may be polar or non-polar. In a non-polar molecule, the center of positive and negative charges coincide. Molecule then has no permanent or intrinsic dipole moment. Examples of non-polar molecule are oxygen and hydrogen molecule, which because of their symmetry have no dipole moment. Okay, so I have already explained this to you, that like this example H2 and O2, they have a symmetry, so there will be no dipole moment, or you can say the positive or negative charges will coincide. The positive or negative charge will coincide like this. Okay, and in case of, on the other hand, a polar molecule is the one in which the center of the positive and negative charges are separated even when there is no external field. Okay, so this polar molecule, they have dipole moment by itself, intrinsic. Even when an external field is not applied, they have dipole moment. Okay, and iconic molecules have a permanent dipole moment, and ionic molecule, such as HCl or a molecule of water is an example of polar molecule. Okay, so now in an external electric field, the positive and negative charges of non-polar molecule are displaced in opposite direction. Okay, so what will happen in case of electric field, like you see here, when there is no electric field, the molecules are like this, but when electric field is applied, the negative charge there will be a force opposite to electric field for negative charge, so there will be a stretching of the molecule. Okay, as you can see from the figure, the displacement is stopped when the external force on the constituent charges of the molecule balanced by the restoring force. But there is also restoring force. They cannot move apart. This molecule cannot move apart. So the stretching will be till then when the electric field, then the force due to electric field is balanced by the restoring force of the molecule. Okay, like rubber band, you can understand. You can stretch it up to a limit, but after that you cannot, because there is restoring force in that. Okay, and now further, so the non-polar molecule does develop an induced dipole moment. The electric is said to be polarized by the external field. Okay, so you will wonder how this electric field is developed. So I'll give an example. Like this is, there is a molecule like this in non-polar. So what will happen? This positive and negative, you see, the negative and positive center coincide. Not coincide, they are very close to each other. The positive or of one molecule is very near to the negative of the adjacent dipole that is induced. Okay, so there will be a neutral charge, or you can say they will neutralize each other. Similarly, this will neutralize, but in the charges on the extreme left or extreme right, on the edges of the conductor, there will be charges on the extremes. Okay, and because of this charges only, there will be what? An induced electric field. Okay, so the electric field is due to this corner ones. Okay, the charges on the edges. Okay, surface charge density on the present on the edges. Okay, so now the non-polar molecule does induce electric dipole moment. The dipole is said to be polarized by external field, and this polarization we called as this polarization, we call it, the phenomenon is polarization. That is, dipole has been induced by electric field. We consider only the simple situation that induced dipole moment is in the direction of the electric field and is proportional to the field strength. Okay, as you understand from the statement that the polarization may take place in a direction a little different from that of the electric field, but we'll take the case in which the polarization is taking place in the direction of the electric field, as you can see from the figure. So there is a term for such type of thing, and that is called linear isotropic. That on isotropic means same in all direction, but here it is linear isotropic means same in a line. Okay, same in a particular direction or a particular linear direction, you can say. Okay, so substance for which this assumption is true are called linear isotropic dielectrics. Okay, the induced dipole moment of different molecules add up, giving a net dipole moment of the dielectric in the presence of external field. Okay, so all this dielectric induced dipoles will add up, and there will be a net dipole moment because of all this induced dipoles. Okay, so now next paragraph is that a dielectric with polar molecules also develops a net dipole moment in an external field, but for a different reason. Okay, in case of a polar molecule, there is also a induced electric field, but in that case there will be a different scenario, as I already explained you, but I will explain again. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation. So the total dipole moment is zero. Okay, so due to thermal agitation, due to the to the energy they gain by a temperature, so they will be having like this. You can see from the diagram. In case of an electric field, there is no electric field. You see the dipoles of the polar molecule are randomly oriented due to thermal agitation. Okay, and but when we apply electric field, what will happen? They will start adjusting in the direction of the electric, like you can see, but there will be thermal agitation even then. So that thermal agitation will try to make them not orient in the direction of electric field, but the electric field exert force so that they can be aligned in the direction of the electric field. Okay, so now yeah, the extent of polarization, when summed up over the molecule, there is a net dipole moment in the direction of the electric field. The electric is polarized. Okay, similarly here, when they will start orienting in the direction of electric field, so there will be a net dipole moment. Okay, and we say that dipole is polarized. The extent of polarization depends on the relative strength of the field tending to align the dipole with the field, and thermal energy tending to disrupt the alignment. Okay, so the what will the external electric field is trying to orient the dipole in the direction of the electric field, while the thermal energy is what is trying to disrupt the alignment. Okay, there may be in addition the induced dipole moment effect as for non-polar molecule, but generally the alignment is more important for molecule. Okay, so like you see, there will be stretching of molecule. This will also happen here, but here the most prominent factor is that of the alignment of the dipole moment in the direction of the electric field. Okay, so the story is that the summary of the story is that there will be a polarization in either case, or whether polar or non-polar. Okay, there will be polarization, net electric dipole moment. Okay, and induced electric field in both the cases. Thus, in either case, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of an external field. The dipole moment per unit volume is called polarization and is denoted by P. Okay, so the dipole moment per unit volume is what? You know the symbol of dipole moment, and dipole moment per unit volume is, we have a term for that, and that is capital P. We denote it by capital P, and it's called polarization. Okay, and how does the polarization depends on electric field? It is dependent for a linear isotropic dielectric. Okay, in the case for the dielectric in which the dipole moment is in the direction of the electric field. Okay, so in this case what will happen? The polarization is directly proportional to electric field. Okay, so we have a constant here, that is xi e, and xi is called electric susceptibility. Okay, so what is xi? Xi is P by E. Okay, that is how much will be polarization per unit electric field. Okay, how much will be polarization per unit electric field? That is called electric susceptibility. It is the property of the material. Okay, so a material having high value of xi will have more polarization with respect to electric field, with the applied electric field. Okay, now it is possible to relate xi to the molecule properties of the substance, but we shall not pursue that here. Okay, so next paragraph is, the question is, how does the polarized dielectric modify the original external field inside it? Okay, so I have already explained you in the previous paragraph, but now we'll see at the molecule level what happens. So let's read further. Let's consider for simplicity a rectangular dielectric slab placed in a uniform external field E0 parallel to two of its faces. The field causes a uniform polarization P of the dielectric. Thus, every volume element del V of the slab has a dipole moment P del V in the direction of the field. Okay, so you can see here in the figure there is a dielectric, and in the dielectric there are, when we place an electric field, what will happen? There will be what we are taking case of non-polar molecule. Okay, there will be dipole like this, and suppose we consider a volume element small v, we consider small element del v. So the polarization in the small volume del v that we consider will be just simply multiply the polarization by the unit volume. As we know what is polarization, it is dipole moment per unit volume. So on multiplying the polarization with the unit vector, unit volume, will get the dipole moment in that particular volume. The volume element del V is macroscopically small but contains a very large number of molecule dipole. Okay, on a macroscopic level we'll say that the volume is very small, but there will be a large number of molecule in that small volume. So there will be a large number of dipole or molecular dipole in that small volume. Anywhere inside the dielectric, the volume element del V has no net charge, though it has net dipole moment. Okay, this is because the positive charge of dipole sits close to the negative charge of the adjacent dipole. As I have already explained you this, you see in this, the positive and the negative of these two adjacent dipole are very close to each other, so they will neutralize each other. Okay, so there will be no net charge inside the dielectric, only charge will be on the edges of the dipole. Okay, so now, however, at the surface of the dielectric normal to the electric field, there is evidently a net charge density. As seen in figure 2.23, the positive end of the dipole remain unneutralized at the right surface and the negative ends at the left surface. The unbalanced charges are the induced charges due to external field. Okay, only the charges on this side and this side, the negative on this side and positive on this side, they will have charges here, induced charges, and they will create induced electric field. Okay, so now next paragraph is thus the polarized dielectric is equivalent to two charges surfaces with induced surface charge densities, say sigma p and minus sigma p. So we can say there are two charge sheet. Okay, the one charge sheet is like this, that has surface charge density minus sigma p, and the other has sigma p, that is positive surface charge density. It can be considered like this. Okay, and now clearly the field produced by these surface charges opposite the external field, there is no need to explain this. Okay, there will be electric field because of this, positive to negative, and that will oppose the external field that is in the direction of this. Okay, the direction of electric field like this, the opposition is like this, so there will be a, but this is not the electric field, induced electric field is less. You can see the reason, because it is only due to the charges on the ends. Okay, and their number is very less. As you can compare, if all the charges are moved, that in the case of a conductor, then the electric field will be very strong. Okay, that is equal to the external electric, but here only the charges on the extreme have the electric field, induced electric field is due to the charges on the extreme, so this value will not equal to the external electric field, hence there will be a net electric field. Okay, that will in the direction of the external electric field, but this value will reduce, you can say. The total electric field in the dielectric is therefore reduced from the case when no dielectric is present. We should note that the surface charge density plus minus sigma p arises from bound charges in the electric. So you can see here no charges are moved, but there is still induced electric field. Okay, so this is the explanation of this paragraph. I hope I was able to make you understand this paragraph. Okay, if you find any mistake in the explanation, please write in the comment section so that others can get that right. Okay, and in the next video I'll try to cover the next paragraph, that is capacitors and capacitor. This knowledge of this will be helpful in capacitance. Okay, so thanks for watching, and please like and subscribe the channel.